Okay, here's a second of two videos about looking at net force. Here we'll have some example, let's say, of forces at angles. So let's say we just have this object here. It's like a disk or something. Okay, and then we're gonna have, for some reason, so this is like a bird's eye view. Okay, here's bird's eye view of this hula hoop. It's a hula hoop. All right, bird's eye view of a hula hoop. And there are three people that are standing in a different position around the hula hoop. Okay, so there's a person over here, and that person, we'll call him person A. So there's a person standing over here. That's not what they look like from bird's eye view, but this is a bird's eye view of a hula hoop, and they have a string attached to the hula hoop right here, and they're pulling with force. Since it's a rope, it'll be tension A. All right, and then we've got somebody else who's like right down here. They have a rope attached to this hula hoop, and they're pulling with tension B. So there's person B. Let's actually make him kind of look like bird's eye view, because it's going to bother me. The arms, person A. All right, whatever. And then we've got one more person. We'll call him person C, and they're pulling like this. Look, this is, here we go, 23 degrees down. All right, so that's where their ropes are attached to this hula hoop. I know this looks nothing like any of the problems we've had, but it's another way for you to visualize our forces at angles and trying to figure out what net force is. All right, so think about this for a second. You have this hula hoop. If I were to draw this as a free body diagram, I would have to put a dot. See, my free body diagram would have, let me use a different color. I'd have a dot at the center of mass of the object. It could be a disk if you want, but the same result, the center of mass of this object for a hula hoop that's a circle is going to be right in the center of it in that open space. And if you drew axes, right here would maybe be my y-axis. So I've got tension B, you can see, will be right along the y-axis in the negative direction. And I could have this be my x-axis. Whenever you have forces at angles, you need to draw axes. Like, you might get away with not drawing them if you have everything orthogonal. All the forces are parallel to the x or y axes. When you got stuff at angles, like, you really need to draw axes, especially if you're on a incline. All right, so that might be the coordinate plane that I choose to use. And you say, well, how are you going to figure out the net force from this information? Because you have people that are pulling in different directions. There are three of them, so you got three forces. And that's why we need to, we say, resolve those vectors. In this case, the force vectors are TA, TB, and TC. Resolve them or break them down into their component pieces. All right, so if I did this once more, let me just put to make an appropriate, an actual free body diagram, I'm not going to have the drawing of the hula hoop there. So let me very quickly rewrite these axes, and I'll draw my forces properly on it. So those are the two axes. There's my x-axis, my y. You can just call up positive and right to the x-axis positive. So we've defined our directions. This will be the same like many of the problems at the beginning of the guided notes where we had something at an angle. I'll just draw my forces in green to differentiate from my axes. So there's the center, my origin. That's my dot for my free body diagram. That's where it is. Here's the first tension. We'll say it's about that long. So there's, you know what, I've been using green for all of the vertical components, so I'm just going to draw this in black so that this is consistent with what I've done in class. So here's our dot for our hula hoop, center of mass. That's our object. We've got a tension force here. That's A. So we call it TA. Tension force B. That's the one that's straight down. Say it's like that far. There's tension B. And then we have tension C was at this strange 23-degree angle that I picked for no reason. All right, so there is that, and it doesn't matter how long it is. It's just an example. So say that these are the forces, tensions A, B, and C. And we need to find a way to express the net force. Okay, so everything's TC and TA are at angles to our axes. Namely, that means to say they're not parallel to either the x or the y axis. TB is parallel to the y axis, so we don't have to break that into parts. I used red as the horizontal, or better to say x component in class, and I'm going to keep that a dotted line because it's not a real, we've drawn all the real forces acting on the hula hoop. They're the solid black lines. So this is a portion of A. Okay, and I recall that this value of the angle was 45 degrees, but let's just call it theta. Now, TB, that's in the negative y direction. I don't have to break that up into its pieces. I do need my vertical piece here for TA. This is where we're making triangles. And you know the way you want to make the triangles when you break up the full force vector here in black into its component parts, you want to make a triangle such that the opposite and adjacent sides from the hypotenuse are respectively parallel to the x and y axes. So my red line is parallel to the x and my green line is parallel to the y. That's what you want. All right, so here we go. TC. See, my green line is going to be the vertical portion parallel to the y axis. So I have to draw it like so. All right, and then I have a red portion that'll be like this. Come on, red, where are you? Trying to cover up those lines. Just do it like that. Okay, and there's the red portion of it. And now we need an angle for this guy. Let's just call it alpha. All right. And I don't need to give an angle for TB because it's not at an angle. It's directly along the negative y-axis because I'm calling up, positive, down, negative. Okay. All right. Whenever we have stuff at angles, we need to give the names of the component pieces. Those pieces in red and green, we have to give them their values in terms of the hypotenuse and sine or cosine of the angle. So this hypotenuse, I'm in the first quadrant, TA, that's where it is. That's going to be TA cosine theta, because that red portion is adjacent to the angle theta, and TA is the hypotenuse, and this is TA sine theta. TB, I got nothing to do with it. So I come over here to TC. That's the one in the third quadrant. I got TC, the hypotenuse, times sine alpha. Different angle, so I got a different Greek letter indicating the angle, and that green portion is opposite that alpha. Then in red, I have TC cosine alpha. Okay, how would we find net force? Well, let's write out our whole equation. Sigma F equals MA, and we're just going to come down vertically and rewrite that equation. We can write it for the x-axis, and we can write it for the y-axis. So here's sigma Fx equals MAX. So if we had the mass of the hula hoop, and we knew the values of all the tension forces, we could figure out what the acceleration of the hula hoop in the x direction was. And then we can go and we can figure out what the acceleration of the hula hoop in the y direction is. And if you know the acceleration of the hula hoop in the x direction is like that, like say that's its acceleration in the x direction, and then its acceleration in the y direction is like that, then you would know, well, from the Pythagorean theorem, I can figure out its total acceleration will be the hypotenuse there. So you take those pieces of the acceleration and add them back up, those component parts, and add them back up to get the total acceleration. So this might look something like what our acceleration for this hula hoop would look like. But let's just go through the process of adding the forces together. So I look in the x direction first. That's what we're looking at first. So on the left side of my equation, I need to look at all the forces that are parallel to the x-axis. Right? It's TA cosine theta and TC cosine alpha. Those are the only things that are parallel to the x-axis. Once I've taken my black hypotenuse, in this case, this is the hypotenuse is the one in black, the full force value. Once I break that up into its pieces, then I'm only looking at the pieces anymore. So TA, we call to the right positive. That's the positive direction, and up the positive direction. So that means I'm going to take TA cosine theta is positive. And in the negative direction is TC cosine alpha. And those are the only forces in the x direction. So then I'd have equals MAX. So there's my true statement about the x direction stuff. Then I would have in the y direction sigma F in the y direction equals MAY. So I look at what things do I have in the y direction. I'm calling up positive. So you can see in the y direction I've got my TA sine theta that points up in the y direction. I have TC sine alpha that points down in the y direction. And I also have, don't forget about TB over there, that's pointing straight down. So since I've said up is positive, I'm going to start with my positive stuff. I have TA sine theta, TA sine theta, let's move it over a little bit, TA sine theta, then minus the other stuff because they're in the opposite direction. They're fighting against TA sine theta. So opposite direction, I'm going to subtract TC sine alpha minus TB, that's also in the downward negative direction, equals mass times acceleration in the y direction. So there's my true statement about that. That's how it add up those forces that are at angles. Now, if it's a problem where it says, but the acceleration is 0, so like the hula hoop's not moving, somehow everything is balancing out. If that were the case, if acceleration in the y and acceleration in the x are both equal to 0, then that means this equation would become TA cosine theta minus TC cosine alpha equals 0. Right? If the acceleration is 0 in both directions and everything is balancing out, everything pointing to the right, TA cosine theta, must balance with everything going to the left. So I'd have TA cosine theta equals TC cosine alpha. And that would be my true statement. If A in the x direction is 0, if I know that, then I can write it. Okay, and then if this one, if they said that acceleration in the y direction is 0, all the forces pointing down, these guys pointing down, have to balance with all the forces pointing up. So if I know acceleration in the y direction is 0, then I would have TA sine theta equals TC sine alpha plus TB. Those would all have to balance out if I knew or were told that the acceleration is 0. All right, so one of the problems that we're likely to see, let's put it more in context of the problems that we have. We have the ground, perhaps. There's the ground. And we have an object on the ground. Okay? And it has some mass m. Okay, and then there's the rope attached to it. And in that rope there's some tension. And maybe there's friction. Okay, and we're saying that, let's say it moves, let's say it's accelerating to the right. So it accelerates rightward. Find the acceleration. Find A. So you're going to solve for A in terms of the terms I gave you, like m, g, mu k, and t. All right? So there's tension force acting on it. There's friction there. We know there's going to be gravity. There's going to be normal force. So we got to set up our free body diagram and find net force. So I know I have Fg. I look at what's the mass of my thing. It's just m. So Fg is mg. I got a tension force that's at this angle. And I said if we got things at angles, you need to have some axes there because I need to show where my angle is. All right, then we have friction. So let's say it's moving to the right and accelerating. That's stipulated in the question. That if that's the case, if it's moving to the right, then I've got kinetic friction because it's moving, and it'd be pointing to the left. And remember this one, we got normal force there, but because we have a little bit of an upward force, the vertical portion of tension, let's call it for a moment Ty, we also have our horizontal portion of tension, call it for a moment T sub x. Since it's a little bit of tension force upwards and it's not accelerating upwards, it's just being dragged across the floor, then we know acceleration in the y is 0, and we'll have to have all our forces balancing. So our normal force is going to be a little smaller than mg, because normal force has the tension in the y direction helping it out. All right, so I want to be able to write Ty in terms of the hypotenuse and my angle. So it's going to be T sine theta, since that green line is opposite the angle. And Tx is going to be T cosine theta because it's adjacent. I've broken up my only force at an angle, T, into its component parts in red and green. And then I've labeled those appropriately with the hypotenuse, the full force, and sine cosine the angle. Okay, let's go. F equals ma. I can do it in the x direction, and I can do it in the y direction. So here's sigma Fy equals MAY. All right, we're mainly talking about finding net force. So we start in the x direction. I see I have t cosine theta, that's parallel to the x-axis, and I have Fk. I'm saying it's being accelerated to the right. So acceleration in the y is 0, it's not being lifted off the floor, but acceleration to the right is not 0, it's something. There's unbalanced force. So if there's unbalanced forces, I say, okay, let's make my bigger force the positive one, since that's going to be the direction of the acceleration. The direction of the acceleration is going to be to the right. That means the direction of the net force, sigma F, is going to be to the right. So let me call the bigger force the positive one. So I'm going to say t cosine theta minus, because Fk is opposing it, it's in the opposite direction. So I'm going to find their difference, equals max. And we can substitute some other stuff in there because we always know kinetic friction is mu k times normal force. So I could write t cosine theta minus mu k times the normal force equals mass times acceleration in the x direction. Okay. Is there anything else I can know? No. We go to the green stuff, vertical direction now. I say, all right, sum of the forces in the y direction. I'm just looking vertically, y direction. I've got t sine theta, that points up. Normal force, that points up. Gravitational force opposes it and points down. Now, in this case, I know that acceleration is going to be 0, but I'll write everything out. Let's just call up the positive direction. Out of t sine theta, that's positive, because it's pointing up. Plus, normal force is also positive. It's helping t sine theta out. They're both in the same direction. Opposing them is what? Fg. So it's opposing it, opposite direction. I write minus Fg. Equals mass times acceleration in the y. But acceleration in the y is going to be 0 because there's no indication of acceleration vertically. It's being dragged across the floor. So I have t sine theta plus normal force minus mg, since Fg is mg, equals 0. And so there are true statements, right? We've got true statements being listed there. If I need to go and find, let's say we're going to look for the, mu k. We want to solve for mu k. Maybe that's the question. We want to get that guy. All right. Well, we need to, anytime I'm asking for this, if you're going to express it in terms of m, g, t, the tension, and theta, and the acceleration, or whatever we're looking for, Fn, let's say we need to substitute something in for Fn. So I'd solve for my normal force over here on the right. So normal force, already positive, I'll leave it there. I'll add mg to the other side, and I'll subtract t sine theta. That'll get normal force by itself, so I have mg minus t sine theta. All right, there's normal force. I can bring it over here and substitute it in for my equation about F equals ma in the x direction. T cosine theta minus mu k times my normal force is over here. Mg, I need parentheses, mg minus t sine theta. That's my normal force. I just dropped it in right there. Equals mass times acceleration in the x direction. Okay. What did I say we wanted to find? Mu k? All right, well, that's not too big of a deal then. I got to get mu k by itself. So I would actually add this term to this side to keep it positive, and then I would subtract max to bring it over there. So I'll do that. You could try solve for a, see what you get. You just divide by m, right? Solve for t. If you got to solve for t, then you got to factor t out somehow. You got to distribute, move it around, factor it out. But I'm looking for mu k right now. Minus max, that would be equal to mu k mg minus t sine theta. Then we got to divide by mg minus t sine theta. So I'd have t cosine theta minus max, acceleration in the x direction, divided by mg minus t sine theta equals mu k. All right, so really in this one, we're just looking at forces at angles and how we find net force. So remember, whenever we have F equals ma, you can look at it in the x and you can look at it in the y direction. If you know the acceleration is 0 in a certain direction, like all of these ones I think where we're dragging something across the floor and it's accelerating, the acceleration is only in the x direction. So you know all the vertical stuff's going to have to balance out. All right, so you add up the forces. That literally means look at your picture and look at all the forces that point in the vertical direction, up or down. If they're pointing in the same direction, they're helping each other out. If they're pointing in the opposite direction, they're fighting each other. So if they're fighting each other or opposing, you're going to subtract them from each other. And if you know the net force is in a certain direction, like in the x direction here, we know the acceleration's to the right, then this force is going to be longer than Fk. The tension force horizontally is going to be longer than Fk. So you're going to have to find the difference of them to get the net force. That's what we did here, t cosine theta minus Fk. And if the direction of the acceleration and the net force is to the right, then just make that the positive direction. So you're taking your bigger force and subtracting the smaller force from it. It's exactly what I did here with t cosine theta minus Fk.